Welcome to The Explainer. Today, we're going to decode one of the most powerful ideas in all of science, entropy. You might not realize it, but this one idea is kind of the secret code that runs our entire digital world, and it's even helping us probe the deepest mysteries of the universe.
Yeah, I know, it sounds like the setup to a really weird joke, doesn't it? But the answer is this single profound concept that lets us measure the invisible world of information, surprise, and uncertainty. Stick with me, and you're going to see exactly how they're all connected.
So to really get a handle on what information is, we've actually got to start with its opposite, uncertainty. Because as it turns out, the amount of information you get from something is directly tied to how surprised you are by it.
Think about it this way. If you flip a fair coin, the outcome is a total surprise. That right there, that's high uncertainty. But what if I give you a two-headed coin to flip? Well, the outcome is always going to be heads. There's zero surprise, and because of that, zero uncertainty. The real information, it turns out, lives in the surprise. And you know, for the longest time, this idea that information is really just about getting rid of uncertainty was just a feeling, an intuition. That is, until one brilliant person came along and gave it a precise, mathematical formula that would honestly change everything. And that brilliant mind? That was Claude Shannon. In this landmark 1948 paper he wrote while working at Bell Labs, he pretty much invented the entire field of information theory, almost single-handedly. Okay, so Shannon didn't just pull the word entropy out of a hat. He actually borrowed it from physics, where it had been around since the 1860s to talk about physical disorder. But Shannon's genius was taking that word and giving it this whole new job, measuring the level of uncertainty in a message. And what did he call this new measure? You guessed it, entropy. To put it simply, Shannon entropy is just a number. It's a number that tells you the average amount of surprise you should expect from any source of information. Doesn't matter if it's a coin flip, a sentence, or a stream of data.
And here is the absolutely crucial part. Entropy gives us a hard number for how much true, unpredictable information is hiding in a message. And that number is measured in the most fundamental unit of our digital world, bits. So think of it this way. A message that's full of surprises, that has high entropy. And it's going to take more bits to lock it down.
Okay, but this is where it gets really cool. Shannon took this big mathematical idea of surprise and applied it to something we use every single day, language. He asked a pretty simple question. Is every single letter in a sentence a total surprise? Well, his answer would change how we think about communication forever. What he found was just staggering. After doing all the math, accounting for all the patterns and rules of English, he calculated that our language is about, get this, 75% redundant. That means 3/4 of what we write and say is actually predictable. In other words, only about 25% of English is true information. You know, the surprising part. The rest is just structure. It's why when you see the letter Q in a word, you're not surprised at all when a U comes next, right? Of course not. That certainty, that predictability, that is redundancy.
And look, this wasn't just some cool trivia fact. This discovery was a blueprint for a total technological revolution. Because if you can measure redundancy, well, that means you can also get rid of it.
And this is the basic recipe for all the data compression we use today. First, you measure the entropy to find out where the real information is. Second, you hunt down all the predictable, redundant patterns. And third, you invent a shorter, smarter code that just throws all that redundancy away. That is literally what's happening every time you create a zip file.
And this really gets to the heart of Shannon's most famous theorem. See, entropy isn't just some vague description of randomness. It's a hard mathematical limit. It tells you the absolute rock-bottom limit of how much you can squish a piece of data down without losing a single bit of the important stuff.
But an idea this big? There was no way it was going to stay stuck in just one field. It just exploded across all kinds of different sciences as researchers everywhere realized they could use this tool to measure uncertainty, well, anywhere.
So you get this whole family tree of entropies popping up, each one a different flavor of Shannon's original idea. Physicists came up with von Neumann entropy to deal with the totally bizarre uncertainty of quantum systems. Computer scientists created Kolmogorov complexity to measure the pure, raw randomness of a single string of data. Each one became this specialized tool for hunting down uncertainty in its own little world.
For instance, you take that idea and you jump over to the completely mind-bending world of theoretical physics. Here, Entanglement entropy is a vital tool for trying to solve the famous black hole information paradox, that huge cosmic question of what really happens to information after it falls past the event horizon.
And what about AI? Oh yeah? Entropy is pretty much the secret sauce working behind the scenes. When a machine learning model is trying to make a decision, it uses entropy to figure out the absolute best questions to ask. It's always looking for the question that gives it the biggest informational bang for its buck, the one that destroys the most uncertainty in a single step.
And you can take that exact same idea and apply it to biology. It allows computational biologists to scan through enormous genomes. By measuring the entropy of different parts of a DNA sequence, they can pinpoint the sections that carry the most important information, helping separate the critical genes from what we used to call junk DNA.
I mean, the list just goes on and on. In economics, it helps put a financial value on information in the market. In engineering, it tells you the exact data rates you need to keep a complex system stable. Even in statistics, it's used to make the most honest predictions when you only have a little bit of data. It's become this truly universal toolkit for dealing with information.
So when you boil it all down, what's the big deal here? It's that Shannon's entropy took this fuzzy, abstract idea of uncertainty or surprise and turned it into a concrete number, something we can measure, predict, and engineer with. It gives us a mathematical handle to grab onto the unknown.
Which kind of leaves you wondering, doesn't it? We've used this amazing tool to master communication, to look into the quantum world, and to build intelligent machines. So as we look to the future, at the incredible complexity of the human brain, or the deepest mysteries of the cosmos, what's the next great uncertainty that a new kind of entropy is going to help us finally wrap our heads around?